It's easy?
Yeah, it's review.
That's true, it's review. Okay, good, I'm happy to do it now. I live for this, but I just didn't want to overload. Okay, so we're talking about action potentials. Remember we talked about that in self-phys. The membrane potential is negative at rest, and then there is this large depolarization during a nerve or muscle action potential. So why is the membrane potential negative at rest? Let's do that over here. We have a high concentration of potassium chloride. This is ultra simple, oversimplified. High concentration of potassium chloride inside the cell, and a high concentration of sodium chloride outside the cell. Why all of a sudden did I put chloride? If I had simply drawn this like this, what would be wrong with that? Ions always come in pairs, right? You never see a cation without an anion somewhere. So this was trying to be more complete about it. Why is the potassium concentration high on the inside? The pump. At rest, what am I drawing here? Remember from self-phys. What are these blobs supposed to represent? Channels. What is special about these resting channels? What is special about these channels that I need to explain the negative resting membrane potential? We did this in self-phys. What type of channels are they?
Channels.
Say again?
Leak channels. Leak channels.
There are leak channels, but what ions do they carry?
Sodium and potassium.
And calcium.
These channels carry potassium. These are highly selective potassium leak channels. So potassium flows out down its concentration gradient. They are highly selective for potassium. They don't allow sodium to flow, and they don't allow chloride to flow. So when potassium flows down its concentration gradient, we now have a net negative charge being moved because a positive ion flowed out and the counter ion stayed in. Okay, do it again. Potassium flows out. Another negative counter ion stays in. Potassium flows out. Another negative counter ion flows in, stays in. Potassium flows out. So the potassium ions, these are K channels, or K leak channels, or resting K channels. Potassium flows out down its concentration gradient, leaving the inside the cell negative. That's why the resting membrane potential is negative. I could get super quantitative and biophysical right now, but I do that in AMP1. So if you want to get biochemical and biophysical, we'll do that in AMP1, not now. All we need to know for right now is that the resting potassium channels make the resting membrane potential negative. The channels and the gradient make the inside of the cell negative. Okay, so now remember from self-phys, what triggered this rapid, very fast depolarization? Well, or maybe let me, before triggering, what is responsible for this rapid depolarization? What's the name of that thing that's responsible for this part of the action?
Sodium influx.
Sodium influx through voltage, gated sodium channels. So we're going to add to this picture here some other channels. That are voltage-gated sodium channels. Let's unpack the name. The name is descriptive. What activates these channels? What turns them from closed to open?
The voltage.
Voltage. Which direction of voltage? Voltage can go up or can go down. Which direction of voltage activates this channel?
Down.
Up. Depolarization. So a stimulus opens voltage-gated sodium channels. Which way does sodium flow?
Out.
In. The sodium concentration is high on the outside and low on the inside. So sodium, let me recolor sodium. Sodium flows in through voltage-gated sodium channels. They are opened by depolarization. And what do they, remember the language, depolarization means less negative or more positive. So they are opened by depolarization, and what do they do to the membrane? They depolarize it by allowing positive ions to flow in. So we've just got a chicken and egg story going on, right? They are opened by depolarization, and they open, and they depolarize. So that is a positive feedback loop. They are opened by depolarization, and they undergo a very fast positive feedback to go to a very depolarized membrane extension. So what that cartoon is schematized by this cartoon. Small trigger opens the channels, influx of the ion, more depolarization, more channels, more influx, more depolarization. This happens very fast and triggers this. Here's the trigger, and here's the feedback loop going on to cause the very large depolarization. Okay? Sodium channels. We're going to see this in the heart, like Wednesday. Okay, so now I want to simplify this. So I'm going to get rid of these guys, just to simplify things. I don't want to restart the thing, but I'm close to it. Okay, so we've now opened the sodium channels and triggered this positive feedback loop that happens very fast and depolarizes the cell. And let's be clear, we're talking about this could be a muscle cell, a heart muscle cell, or a skeletal muscle cell, or a neuron. What happens to sodium channels? You'll remember this from self-phys, I hope. What happens to sodium channels after they open and after they all undergo this loop? There's a word for what they do. No?
They get inactivated or closed?
They inactivate. So they undergo another conformational change. The voltage opened them, and then they inactivate. So they go into they spontaneously go into a refractory or inactivated state. And so there is no longer the sodium influx. I mean, we still have, the cell is still depolarized. The cell is still depolarized. But there's no longer the influx because of inactivation. The feedback loop is broken. What else did this depolarization, so the depolarization caused the channels to open and then inactivate. What else did the depolarization do? Give me the next slide. Something else that this depolarization did. Anybody? Easton.
Doesn't that open up the potassium channels?
It opens up, did it open up the same potassium channels that we had up here a few moments ago?
Now the voltage you.
Now we have a different population of potassium channels that I'll illustrate with a different color. It opens up a voltage-gated potassium channel. Well, more than one, a whole boatload of them. Which way does potassium flow? Out, just like it always does. Potassium flows out, leaving behind a negative charge. Potassium flows out, neutralizing, leaving behind a negative charge. Potassium flows out. What did we just do? We just went from depolarized back to negative or repolarized. So the depolarization opens voltage-gated potassium channels, potassium flows out and makes the cell repolarize. Why do I say accelerates and not just causes? What else could have caused the repolarization if we didn't have these voltage-gated potassium channels? If the sodium, remember the sodium channels open and then inactivate, is the cell going to stay depolarized or is it going to repolarize? If you shook your head, you're right. Why would it repolarize?
Because the action potential finishes, terminates, and then you're at repolarization.
Yeah, the action potential is over, but what caused, if we don't have voltage-gated potassium channels, what would cause the repolarization? It will happen, but why?
You run out of sodium channels to be activated,
The sodium channels are inactivated,
and the leak channels.
and the leak channels, the resting channels are still there. So there's always a way for potassium to get out. It's just that these voltage-gated potassium channels assist and accelerate the repolarization. So now you have a nerve or a muscle action potential. On Wednesday, I'm going to add calcium channels into the mix, and you'll get a cardiac action. But now, and it looks harder, but it really isn't much harder. You're going to see depolarization due to sodium channels. You're going to see repolarization due to potassium channels, both of which are voltage-gated. And you're going to see a plateau that is due to calcium channels. And that's the only thing. So medical students get so bent out of shape about cardiac action potentials, and it's really just adding one more thing to a nerve action potential. Okay, good. Thank you for letting me do this today. We're good for today. On Wednesday, please do, so what I want you to do is look at the problem set. Maybe rewrite your notes. I want you to go back to the Moodle. Go to Moodle and look at the PowerPoints. I'm actually right now going to strip out the answers to those open questions so you won't have them anymore, so that you can work on them. Well, let me ask you a question. Which would be better for your learning? To go to the problem and work on it, and then be able to check the answer right away? Or would it be better for you to work on the problem, to not get the answer, to work on it as a group on Wednesday, and then I expose the answer? Which would work better for your learning? The first one. Okay, so I'm going to leave things alone, but that means that you can't just look at the answer. You have to struggle with the problem and then check your answer. That's what you have to do in order to learn well.